All right, it's 1 o'clock here on the East Coast. We're going to go ahead and get started. We've got a lot to cover today. Good afternoon and evening, everyone. Welcome to AFL's Mastering Advanced Fiber Splicing with AFL's ARCMaster FSM-100P+. I'm Charlie Collius, the Global Product Marketing Manager for the equipment group here at AFL. We're delighted to have you all here today taking part in our webinar. So before we begin, just wanted to go over some housekeeping tips. So all attendees here are in listen-only mode to reduce the background noise during this webinar. Throughout today's presentation, please feel free to submit any questions you have using the questions box in the control panel you can see on your screen. We'll answer these at the end of the presentation, so don't hesitate to ask them during the session. So today's webinar is also being recorded and should last about 50 minutes, and then we'll go into Q&A. A link with where to view the recording will be sent out tomorrow. So right now, it's my pleasure to introduce Craig MacMillan, who is our presenter today. Craig is an application engineer for the Specialty Splicing and Accessories here at AFL and has an extensive background in optical sciences. He works alongside our sales team, repair group, and customers to solve day-to-day splicing challenges experienced out in the field. The FPS 2.0 software that Craig will be using, you'll see this on your screen. He'll use this with the ARCMaster today. It's a free download and it's available on AFL's website under our resources menu. It's 100% free. It's very easy to use, and you will see it allows complete control over the splicer and has a great, beautiful user interface. So I'm looking forward to seeing this session today and the demo. So Craig, I'm going to make you the presenter here, and then you can take it away. All right, anytime you're ready, Craig. Thank you.
Thanks, Charlie. Can everyone see my screen? I think you're still sharing your screen, Charlie.
Really? Let me do this. There you go. Sorry about that.
Yeah. Hey, everyone. My name is Craig MacMillan. Thank you for the intro, Charlie. Today, we'll be going over the FSM-100P+. I chose the P+ specifically because it has features that all of the other splicers have as well. So we're not going to miss anything that something else has. And like Charlie mentioned also, we'll be using FPS to facilitate this, so you can get a feel for the software and get a feel for the capabilities of the splicer and everything that you can do with it. So without further ado, I'm going to go ahead and jump into just a general overview of splicer components, what's under the hood. We'll transition over to FPS, and I'll give a brief overview of that. And then my plan for today is to walk through essentially how would I create a splice mode for a non-standard fiber, right? Today I'm using a Fujikura multi-core fiber specifically as the example, right? It's a non-standard fiber. It requires different alignment considerations than you would typically find, So I'll walk through that, give a brief overview of the splicer as a whole, and as Charlie mentioned, at the end, we'll open it up for questions. So I'm going to go ahead and jump into it. And let me switch my view here. All right. So in front of me, I have an FSM-100P+. Right? This is the fusion splicer that allows rotational alignment, right? And it also allows for an additional sweep range as well, seen by the scale here. You can slide the fiber holders back and forth to accommodate larger diameter fibers. So just for anyone who may be unfamiliar, let me zoom in a little bit. I'll go over the components and then we'll switch over to FPS, right? So the first thing you'll notice is right there in the middle of the screen, you've got your electrodes, right? This is where the arc originates from. And on all of the FSM-100 models, these electrodes can be spaced between 1 and 3 millimeters apart. However, on the plus models, these electrodes can also oscillate up and down to accommodate larger diameter fibers. Because even if the electrodes are 3 millimeters apart, you can only have a plasma field that's so large. And so you need to physically move the plasma field in order to evenly heat a fiber, right? And so these plus models will allow you to swing the electrodes up and down, as well as adjust the gap between the electrodes depending on your fiber size. All right, and while we're focused here in the middle, the next thing you'll see is a unique feature of the plus models. Right, below the electrodes, you can see there's a little circle here, and that circle is actually a periscope mirror, where when you are using an end view capability, that mirror will move up between the electrodes and allow the fiber's end face image to be reflected through that mirror and down into one of the cameras, which are right here on either side below the electrodes. You may be able to see it. Right, and so using that method, you can get the actual end view image of a fiber. This is very useful specifically for cases where the fiber is either new, it's not known, or there may just be some sort of uncertainty in how it should be aligned, or maybe it's too complex for the side view to align it, right? And so you need to use the end view image to properly align the fiber. But in many cases, this can also be used for things like verification. Maybe there is maybe you have a specific fiber that you don't know exactly what kind of PM fiber it is, right? Someone may say it's a Panda fiber, but you just want to double check to be sure. So you can put your Panda fiber in here and verify, okay, yes, this is a Panda fiber, right? And then moving outward from the electrodes, we can see that we've got our V grooves on either side, right? In the splicer menu, these are listed as your VA and VB V grooves because this is a split V groove block, right? And what this allows is the splicer to physically resize the V grooves based on the fiber size that's loaded, right? So if you load a very small fiber size, the V grooves will close down to accommodate the smaller diameter. Or in the case of the P+, if you load a larger fiber size, those V grooves can open up to accept up to 1,250 microns in diameter, right? With the 100P, that diameter is limited to 500, right? You don't want to go larger than that because the electrodes can't swing, right? And then you have problems with uneven heating, et cetera, right? Lots of trickle-down effects. Right. And so these two halves of the V groove can move independently of each other in order to accommodate that, right? And then the counterpart to the V grooves is your clamp chips up above here, right? And these are linked to your wind protector motion. Now, right now, I have the wind protector all the way open. Right? This is how you would have it if you were cleaning the mirrors, for example. But what this allows you to do is this allows you to fully see the rear electrode, the rear electrode mounting block, as well as the chip clamp mechanism, right? You've got your actual clamp here that moves up and down, and this clamp can slide from side to side as well to accommodate different positioning of the V grooves, right? And you can also manually lower these to verify the position of your fiber, make sure it's going to sit correctly in the V grooves before you close the wind protector. Now, an important thing to note here is while you can do this, the wind protector is not going to close in this configuration, right? So if I put both of my clamps down and try to close the wind protector, it's not going to close, right? The splicer will act like it's trying to close, but it still won't close because the wind protector is physically being blocked from closing, right? So in order to close it, I'll have to open these. However, right, they are independently operable and they are motorized. So when the splicer closes the lid, these clamps will physically move down to apply clamping pressure onto the fiber, right? And then continuing further outward, we have the Z stage. Right, this is intuitively where the fiber holder itself sits. Right, I've got my fiber holder right here, and I'm just going to drop it right there on the guide pins to locate the fiber holder and place it in position, ready for use, right? And so this is where a fiber holder normally would sit, right? Now with larger diameters, we generally recommend up to like 250 microns and larger that the fiber holder actually be loaded the other way. However, on the Plus models, that's not so much of a requirement, right? Because not only would that mean you have to remove the LED unit, right? But the reason it's not a requirement is because you have the additional capability of this Z stage adjustment, right? So if I zoom out, you can see I've got this scale that goes from 4 to about 40 millimeters, right? So if I just loosen these finger nuts right here, what this will do is this will unlock the Z stage from its parent mechanism, allowing you to slide it backwards and forwards, right? So for example, if you are using a 1000 micron rod, right, and you're performing some sort of shaping operation with it, you would want to scoot this all the way back. You can hear how southern I am. I just said scoot. You can move this all the way back to give that fiber some room to flex. But if you have a smaller fiber like this that I have here, this is just a 125 clad 250 coated fiber. You don't need to have it all the way back there, right? And in many cases, you won't want to have it all the way back there, so you can have it all the way forward. Right? So I'm just going to leave this up here. And the last thing, or actually second to last thing, two more things I want to mention about this is what you just saw me open. That is the end-view LED unit. Right? So you can see the fiber image, right, by having a mirror there, but you can't see anything if it's not illuminated, right? And so what this LED does is it'll shine a very bright light on the side of the fiber to inject light into the fiber, right? And then let some of that couple with the cores and let some of it be guided by the cladding for this short distance so that you have an illuminated image on the actual cleaved end of the fiber. And then the last thing I want to mention is your theta unit here. This is what will physically give you the ability to rotate the fibers, right? So if I back out and go to my motor drive function in the splicer, I can turn both of these, right? And this will allow you to get PM alignment capability using the functions of the splicer, right? You can physically rotate the fibers to match your axes to each other. So a quick overview of the splicer components, right? There's obviously a lot more complexity to it, but for the sake of time, I'm going to go ahead and stop there. And now I will dive into the FPS, right? And so right here, I've got my FPS pulled up, right? And I have two windows pulled up. And these are the two I'm going to focus on for right now. There's a lot more to FPS. So I'll give a quick overview, but I'm not going to go through it in depth, right? I'll focus mostly on these. But your data collection app, right, is where you'd be able to actually collect data from the splicer, right, and then store it, analyze it, use it later, right? And we'll be using this. I'll be using this to actually show what you can see after the splice, looking at the rotation alignment data, right? And then on the other hand, I'll be using the live video module, which allows you to basically simulate actually using the keypad of the splicer using buttons. Now, unfortunately, this is not interactive, right? However cool that would be, but you can still use all of these keys exactly like they would work on the splicer. All right, so I can hit the menu button and go to my splice menu, right? This is the actual screen that my splicer is displaying right now. And use my arrow keys to navigate up, down, left, right, back out, or I can go use my shortcut key to get to the motor drive. I've set that as my shortcut for the escape key, or I can hit set to begin the splice, just like normal splicer controls. Excuse me. So what we'll do is I've already got some fibers prepped. And what we're going to do is I'll do a quick walkthrough of the splicer parameters, and then parameters, functions, menus, and then we'll get into actually making a splice mode. Right? From scratch, we'll go through, okay, I've got this multi-core fiber. What do I need to do in order to get started with splicing it? Now, obviously, the optimization process is much more complex. But what this will do is give you the ability to handle some of the preliminary considerations before you dive into the details of things like arc power, arc time, stuffing, and all those other very important concerns, but those are more optimization related. What we're talking about is splicer capability and preliminary considerations such as rotation alignment, right? And we'll focus mostly on that because it's definitely the most complex and one of the most important, especially in the realm of things like multi-core fibers, for example. So what I'll do is I'll just do a quick step through of these menus here, just give a brief overview of some of the highlights, and then we'll go back to our select splice mode menu right here, and then dive deeper into that for the content of building a splice mode. Right. So in this select a splice mode category, this is where you go to actually find, what are your saved recipes. Obviously, you select which one. Now, you can toggle pause 1, pause theta, and pause 2 during the splice, right? These are specifically for you to have the ability to inspect what has the splicer seen so far, right? At each of these states, the splicer will stop and say, okay, at pause 1, it looks at the cleave angle, right? So you can say, okay, is my cleave angle good or bad? And you can be the judge, or you can set a alarm threshold inside the splice mode to where, hey, if my cleave angle is larger than 2 degrees, it'll reject it. Or at pause 1, I can have it display the cleave angle and say, hey, this is what your cleave angle is. And then you can choose to go on or hit reset, start over, get a better cleave, and continue. Likewise, pause theta stops immediately after the rotation alignment is complete, and pause 2 is the last stop before the fibers are actually burnt together using the arc. Some of these I'll kind of skip over a little bit for the sake of time, but one thing I will mention is, especially in production environments, it can be helpful to have the auto start turned on. Right now I have it off just because I don't want the splicer to start going without me telling it to. But whenever you close the lid to the splicer and it's in the ready state, it will take that as, okay, time to start splicing, right? It'll take that the same way it would if you hit the set key, right? So this is one thing to keep in mind. This can be really helpful, especially in a manufacturing environment, where you're doing a large quantity. I won't talk too much about the heater mode section, other than based on the different heating parameters that you have, you can heat different sleeves, right? Your 60 millimeter, 40 millimeter shrink sleeves for protecting your splice. Maybe you don't even use shrink sleeves, right? Maybe you recoat instead. But same thing as with the splice mode, had this auto start function. The heater mode also has that auto start function where instead of needing to press the heat key every time you want the heater to start going, as soon as the heater oven closes, it'll take that as a trigger. Hey, I need to start heating up the sleeve. Now, these settings are generally where you'll go to say, okay, how do I interact with the splicer and how does the splicer generally interact with fiber, right? Splice settings handle, okay, how does the splicer interact with the fiber? what does the splicer do as it's handling the fiber, right? So these are things like, okay, what information does it display at the pause, right? What steps does it take between pauses, right? And then under maintenance settings, right, this is where you can set your maintenance alarms depending on what your use case is or what your application. And then machine settings is where you go to see how I interact with the splicer, right? These two, the splice settings and machine settings, are the two frequent flyers as far as what, how do I fine tune my workflow when I'm using this. Number one, I want the splicer to handle the fiber properly, but I also want to be able to interact with the splicer in a way that suits my work style, right? So machine settings is like, how loud is the beep? What language do I want the machine in? You know, things like that that allow you to choose, okay, what's the best way for me to interact with the machine? And from the factory, all of these come with a password, but that password is simply 0 and then enter, right? And then I can get in, I can say, okay, I want to ignore some errors and do whatever setting changes I need to do. But the password for all those from the factory is 0. Now under menu lock settings, you can change that as a supervisor setting. And then your fiber type compare and auto arc calibration are sort of similar, although they are different applications of the same sort of technology or same sort of analysis. Your fiber type compare will look at the side view of a fiber and say, hey, this is what the side view of this particular fiber looks like. This is what the side view of an SMF-28 looks like, or a HI-1060 looks like. Right, and then you can use that to automatically discriminate between one fiber type versus another fiber type, especially again in production environments where you want to make sure that the correct fibers are being spliced, right, and the correct parameters for those fibers are being used, right. And similar to that, auto arc calibration will, instead of using a cold image, it will use the warm image of the fiber to determine, okay, how hot is the fiber, right? So instead of scanning the vertical image of the fiber like a barcode, right, what we're doing is we're looking at the brightest point of the fiber along that vertical scan line and saying, okay, this is how bright this fiber should be when it's at its correct heated state, right? And so you can go into this auto arc calibration menu and train the splicer on, okay, this is what a SMF-28 should look like, right? And then you can use that arc calibration reference in your splice mode to say, okay, I'm splicing SMF-28. This is my reference. Now that's not a substitute for a daily arc calibration to get you started on the right foot, quote unquote. But what this will do is this will keep you on the right foot, especially if you're in an environment that's not very tightly controlled, right? Because things like temperature, pressure, humidity can all affect how much power is required to adequately melt fibers, right? And then the other important thing that I want to touch on here is the IPA data. For fibers that require rotation alignment, especially new fibers, multi-core fibers, this fiber I have here is an example. This is where you go to teach the splicer a new fiber, right? So if I go into here, I can say, okay, user-definable IPA data can be registered using this function, refer to the instruction manual, and you can use this function to actually teach the splicer new IPA data, right? If I have a multi-core fiber that's never been used before, I can put it in the splicer will analyze it, I will pick the ideal alignment position, and then I can say save, right? And then I can go back to my splice mode and reference that specific model that I made and say, yeah, I'm using this fiber, right? And then I can use that model to align two fibers together, right? So, and I need to speed it up here, but so on these last two maintenance pages, I'll just talk about the arc calibrations. and then I'll mention some brief maintenance tasks. So ARC calibration is standard, just standard ARC calibration. This is always done with SMF-28, 125 micron clad 250 coated SMF-28. Right, what this will do is it will purposefully offset the fiber, then watch how quickly those fibers self-center using the viscous self-centering effect of surface tension. Because just like any other liquid that has a surface tension, melted glass is also a liquid and it has a surface tension. And as such, we'll want to pull the fiber's axes into alignment. Right. Now, special ARC calibration, on the other hand, is different because it does not actually splice the fibers together. What it'll do is it'll bring the fibers in and then shoot a couple short arcs to watch how quickly the corners of the fiber round over. Right? And measuring the change in that radius per arc will give the ideal arc power as a function of that specific fiber type. Now, what special ARC calibration allows you to do is it allows you to tie a specific ARC calibration power to a single splice mode and isolate that from everything else. Because every time you do a standard ARC calibration, it adjusts the baseline ARC power for every splice mode in the splicer. Right? It adjusts the baseline ARC power for everything. But if you have a certain very small, very sensitive, or very large fiber combination, that requires different heating parameters or uniquely sensitive heating parameters. For instance, if you're splicing a 40 or 50 micron fiber, something that does technically exceed the limit on the low side of what the splicer can handle, right? You'll want to use a special ARC calibration. Even with like 80 micron fibers, you'll want to use a special ARC calibration because those fibers are smaller, they're more sensitive. And instead of basing it on that standard ARC calibration, which can have larger, swings. What you'll want is you'll want to base it on your special ARC calibration. That way, that value stays the same, even though you'll do an ARC calibration with a single mode fiber for another splice mode, right? And then the one thing I'll note, two things I'll note on this page are the diagnostic test and the motor calibration, right? These two are pretty important, right? Your diagnostic test will take you through all the primary functions of the splicer, and basically, I like to call it like a checkup for your splicer, right? It's basically just a quick test of everything. Is everything working correctly? Have you do an ARC calibration? You will look at the lenses to see if there's dust on them. It'll check the background brightness evenness, right? So if you look over here on my other screen, the X and Y images over here, it looks at how even is the brightness across this whole field of view, right? This is my background brightness, right? And this is what's going to give me my image when I put a fiber in front of it, right? So, and then, so it'll run through all those functions and make sure everything's working correctly and identify any problems that are happening, right? And then as part of that, it'll do a motor calibration. But one thing that can happen is if you start seeing any motor issues, the first thing to do is do a motor calibration, right? Because it may seem a little bit counterintuitive, but since the motors in the splicer are stepper motors, right, they are programmed to run at a certain speed for a certain time, right? You're not necessarily saying, okay, move 10 microns forward. What you're saying is move forward at 10 microns per second for 1 second, or 100 microns per second for 1/10 of a second. Right, and so what motor calibration will do is it'll calibrate how fast those motors are moving, right? Because you can measure distance using a known pixel spacing on the image, right? And so by moving the motors in view, it can move, okay, I want to move 10 microns, and it'll move the fiber by what it thinks is 10 microns, and then measure ending position from starting position and say, okay, this is how far it moved. Right, and then based on that, you can adjust the speed to where it gets the correct motor speed from that movement requirement. Right. So, quick overview of the menus. Let's go ahead and dive in to making a splice mode, right? So I have two multi-core fibers, right? They're both 4-core multi-core fibers. It's Fujikura step index, 4-core multi-core fiber, and it has a marker, right? And the first consideration is, okay, what splice mode am I going to base it on, right? So this is just basically what you'll see when you open up the splice mode screen for the first time, right? So I'm going to base it on PM Auto 1, right? So I'll just start here. I'll hit edit. So what I'm actually doing, you'll see I just changed, but I wasn't hitting any of these buttons. You can drive using the soft keys, or you can use the keys on the splicer to drive as well, right? I can use the keys on the splicer to move, and I can also use the sheet keys here in FPS. Right, so that'll work either way. Just wanted to say that. So as soon as you go into edit the splice mode, first thing you'll do is check your fiber type. Okay, right, so using PM Auto 1, it'll take all of these parameters from PM Auto 1 and use those to base the recipe on. Now, what I'm doing with this particular fiber is I have the coating of the fiber in the V grooves because I want to have a shorter cleave length, right? So maybe I don't want to base it on PM Auto 1, I want to base it on PM Auto 2, right? Because the difference between PM Auto 1 and PM Auto 2 is the cleave length right here. Right. It's just a quick way to switch between two different cleave lengths with the same parameters otherwise. Right. So I'm just going to start here. This is what I want to do. It'll say, do you want to reset everything to its original factory values? Okay, yes, I do. So I'm at PM Auto 2, right? And I'll start by making sure my arc calibration method is standard. And then I'll go straight over to my fiber settings for my left and right fibers, right? I've got page 2A and 2B right here. These are my left and right fiber information pages. And I'm going to make sure that my coating diameter is correct. That's correct. It's 250 microns. The cladding diameter is correct. It's 125 microns. Now, I do have a multi-core fiber, right? It does have this same 8.2 micron core. However, I'm not doing core alignment. Right, so these two parameters, your core diameter and your mode field diameter parameter, are for the purpose of calculation. Right, so if you're doing a core alignment splice, like a single mode fiber, what you'll do is you'll want to make sure these are absolutely accurate. I just say it's a good practice to always put these in there correctly. That way, when it does matter, you don't have to worry about it. Right, and so these are used in the calculation for coming up with the loss estimation number at the end of the splice. Now, since this is a multi-core fiber, we'll be using cladding alignment, right? And you can see that's over on the summary screen. This is basically a summary of the splice mode so far. Right, I've got my 1 millimeter electrode gap. My fiber is directly in the middle. My XY alignment set to clad. You can keep track of everything that's happening over here. And then my cleave length, this is how much exposed glass is on the fiber when I pull it out of the cleaver. Right? When I'm all done, how much exposed glass is there when I put the fiber into the splicer. Right? And so 4 millimeters indicates that I will have the coating sitting on the V grooves. Right? So what I could do is I could go up to my clamp at parameter and say, coating, right? And then I have basically forced it to say, yep, I'm clamping on the coating. It's always going to assume I'm clamping on the coating, right? And so then, and I'll actually leave this set to clamp at coating, and I'll leave this on auto just to show that it does the same thing. Right? And then my right fiber is the same. So I've got my coating diameter, clad diameter, core and MFD. Those are the same. Cleave length is good. Okay, checks out. Now, what I will do, I'm going to go over to page 4, A, B, C, D, right? What these pages are, this is where you go to choose your alignment method, right? Alignment method, alignment mode. What this is when you have a certain fiber, your splicer will use a variety of methods to analyze the fiber, right? If you have a P plus, like I've got here, you have some more options because you have end view, right? You can either turn your theta alignment off and say, I don't care about rotating this fiber. It's a single mode fiber. It's the same anyway you turn it. Or I can use PAS, which is Profile Alignment System. Right? This is essentially, I'm looking at from the side. And these are the X and Y cameras that I pointed out earlier. Or you can use end view. Right? This is where instead of rotating the fibers from the side view, they'll instead immediately back apart, and then you'll look at one fiber, look at the other fiber, rotate them to match using image analysis, right? And then splice that way. Or you could use a power meter, or you could use EV lock. Now, what's the difference between EV and EV lock? Right? EV just allows free rotation of both fiber holders across the board, right? They will both align to the optimal position. But EV lock is specifically for the case where you have, for example, a sensitive component on one side that cannot be rotated, right? So you'll put your sensitive component on one side and on the stationary side, and then that side will be analyzed first using the end view. Right? And then your pigtail that's being spliced onto that will go on the other side, your movable side, and your movable side will be moved to match the stationary side. And that's where it'll align, and that's the reason why it has to use end view as well, because if you're not going to rotate the fiber, you can't gather data on it, right? That's the whole way PAS works, and that's what we're going to use here is PAS. Now, which alignment mode am I going to use in PAS? Right, so within the set of PAS, there are several subsets, right? I could use a specific Panda mode, right? I could call out a certain reference model, right, for these. I could use Panda mode. So Panda will look for symmetry in the fiber, right? And it'll align the fiber using the symmetry of the fiber itself, right? IPA is Interrelation Profile Analysis, right? Where you choose a reference point on where a reference point is chosen on the fiber, and as the fiber is rotated, data is gathered on it, right? Or IPA2, which is an improvement on IPA, which uses some Gaussian smoothing and an additional or different reference point, right? Or some other alignment modes based on specific fibers that have been used in the past, right? A lot of times, for example, Panda 3 tends to work better for 80 micron fibers just because the lensing effect is different, but sometimes you just have to experiment. And also, finally, there's an angled cleave option for matching cleave angles. For instance, where you don't have the ability to splice more than once and you don't care about polarization so much, but for instance, you're length constrained, what you really care about is the difference between the cleave angles, not the gross cleave angle itself. Right, so if you can minimize that difference, a 2-degree cleave angle and a 3-degree cleave angle, if you match them, that becomes a 1-degree cleave angle difference, which is absolutely spliceable. Right, by any standard. So for this, I know multi-core fibers really like to use IPA2. They tend to work very well, right? So I'll select that for both of these. And again, we're going to speed up some. So I'll check IPA2 for both of those. I know they work well. And then I'll move to the next page. I want my rotation step angle to be 3 degrees and my total rotation angle to be 360 degrees. And my max alignment angle, I want that to be 360. Basically, I want each data set to be able to overlap on the very tail of the other data set, right? And so under IPA settings, this is the last one I'll cover in the splice mode for right now, and then I'll actually show the splice happening, right? This will be your specific settings for each fiber, right? Your method is, okay, do I want the splicer to compare each individual fiber to a reference model, or do I want it to compare the left fiber to the right fiber, right? Do I want to just overlap these two the best way they fit, or do I want to compare the left one to a certain reference model that it fits best with, and likewise with the right fiber, right? And so if I choose different fiber, then I have the reference model option. But if I choose same fiber, then my left and right go away, right? Because I don't care about left and right anymore. All I'm trying to do is match both of them up, right? So I want to use different fiber, even though this is the same fiber on both sides. I want to use the reference model because I want to see what it is. And so basically what I'm doing here is I'm saying find best. This is, I want the splicer to look at this data, compare it to everything that's in its internal database, find the one that has the best statistical fit percentage-wise, and use that reference model for aligning this fiber, right? Right, and then for additional theta alignment, I'm going to turn this on, right? So this is after my side view alignment, I'm going to use the end view, right? And then for demonstration purposes, I'm going to set it to manual for focus control. Now, I'm going to go ahead and back out and we'll run with these parameters. And so I'll select my PM Auto 2 splice mode, right? And I'll go ahead and hit set. And we'll see the fibers come in, be inspected, pause 1, then we'll move to pause theta, and then pause 2. So now you can see the fibers come into the field of view. They are initially inspected, right? We've got our cleave data and then fiber angle data right over here. We've got our left side fiber on the X view, 0 degrees, Y is 0.2. Same with the right, 0 and negative 0.2. Aggregate XY is 0.2, 0.3. There's another digit here that's not shown. It's because, and so this ends up being a rounded digit, but you can extract this digit using our communication API. And then your fiber angle data, right? So this is your cleave angle, right? This is the angle of the end face relative to the fiber's axis. And then your fiber angle data is the angle of the axis relative to perfectly horizontal, right? And so these all look very good. Ideally, I would want this XY to be a little bit better, but that's still very workable. So I'll go ahead and move forward. Now we'll do my theta alignment. Now, what you'll see here is what the splicer will do is you'll see it taking steps, right? And the reason for this is because I told the splicer I have the coating of the fiber sitting in the V groove, right? If the coating of the fiber is sitting in the V grooves, what will happen is a lot of times the friction coefficient between the acrylate coating or whatever coating it is, most of the time it's acrylate, between that and the ceramic V groove is pretty high, right? Especially when it's captured by that clamping pressure from the clamp above, right? And so what happens is instead of spinning freely in the V groove, right? Because recalling back to the image of what the V groove and Z stage looked like, the V groove doesn't rotate along with the Z stage. Right, the fiber holder will rotate, but the V groove stays still. And so, if you have a lot of friction between the fiber and the V grooves, it's going to twist, right? Which means when it takes 3-degree steps, like it's doing right now, the fiber itself won't actually rotate 3 degrees each time. Right? If I have everything clamped and I'm doing continuous rotation. Right, it's not going to move 3 degrees at a time, and so maybe every 10 or 15 degrees, it'll take a big jump and catch up, and then it'll twist again until it can overcome that friction and jump again, right? And so what the splicer will do is if you tell it that you're clamping on the coating, right? If you have the coating sitting in those blue V grooves, then it'll get set to the starting position, capture an image, open the V grooves and raise the clamp, rotate 3 degrees, close down the V grooves, close down the clamp, center and refocus the fiber, right? Because you can see there are some things happening. You can look at both the X and the Y images. Every now and then the splicer will adjust the fiber and refocus on it, right? That's what we're talking about. It'll readjust the fiber into the correct field of view so it's getting the right data point. Right? Because if you think about it, the fiber's position in the field of view will directly affect the image that we're seeing here, right? This brightness width right here, this is dependent on the fiber's position in the field of view. So if the fiber doesn't stay in the right spot, this is going to change. And so we want the fiber to stay in exactly the correct location in order for this field of view to be correct, right? So as this wanders, after a step or two, right there, see that it corrected, right? Because you could see some of that error in the alignment of the machine being compensated for by the rotation, right? Now, for like a simple fiber, like a panda fiber, for example, you can easily use continuous rotation. If you tell it that you're clamping on the cladding of the fiber, then it will rotate continuously, right? Because the glass has a very low friction coefficient between the V groove, right? And so it's gonna slip really nice. It's not going to twist and make those jumps, right? So right here we can see the splicer analyzing the fiber. It found the on the X, or not on the X, on the left side, the fiber was a 4-core step index clockwise, right? And the same for the right fiber, it was the 4-core step index clockwise fiber, right? And so what that is right there is we're looking at the polarity of the multi-core fiber, right? And so right now, since I turned on the additional in-view alignment, my in-view module is popping up. And it's going to show us what our fibers look like, right? So I'm going to hit the escape key to remove these paint crosshairs, and then I will drive the focus right. Now I've got my focus in position. I'll use my Y motor to move that up a little bit to center it a little better in the frame. And then I'll use my XY to switch sides. All right, so this is the end view of the actual fiber that I have in here. And what you can see is it looks like these have little trenches around it, right? But in reality, what you're seeing here is we're seeing some higher order modes pop up in these cores, right? Because these cores were meant for near infrared, right? Your telecom 1310, 1550 wavelengths. However, the much shorter visible wavelength will generate a few first or second order modes in that core, right? And so we're seeing some of that injected visible light generating some higher order modes, right? And you can see this with panda fibers as well, or any single mode fiber, traditional telecom single mode fiber that you put in the splicer, is it will you can start seeing some of those higher order modes develop as a result. Here we go, that's good. And I'll use my menu key up here to adjust the LED brightness because that other side looks pretty dim. Right, and right here we can see, yep, we've got both of those fibers aligned. Right, and your escape key will just toggle between those. Right, different graphs, and those graphs are used for your actual, like if you wanted to do alignment using the end view, that's how you would do it. You would use those graphs as your reference, right? That purple crosshair overlay. So we've got a good visual here. Okay, I can inspect this. I can see the polarity of this fiber, right? I can see here's my marker, here's core 1. Right, and then I can use this to go to mark my polarity. Okay, this is core 1, 2, 3, 4, and this one matches. This is my 1, 2, 3, 4. If the marker was over here and I lined my cores up, then I would have core 1 going to core 4, right? And likewise, core 1 over here going to core 4 over here, right? That's your typical polarity scrambling from a multi-core fiber, right? So I'll go, I'll hit the set key to proceed past this, and we'll let the splice go through. I'll show you the graph in FPS of the splice data that we captured, and then we'll open it up for questions because we're going to end up just a little bit over, but we'll get as many questions as we can. I really want to show this, really want to show the results of this splice here. So right now our in-view motor is resetting. capturing any data that it needs to from these images. And we're going to see it move into our final pause 2, then we'll splice it and then perform the estimation. All right, so here's our gap set. We'll see the splice complete after pause 1, or pause 2, I mean. And then we'll go into estimation. And while this is estimating, we can go ahead and start taking questions as this is running. You know, I might during the questions, once we get to the end of the estimation here, and I have the data to show, I'll interject real quick. But Charlie, if you want to, yeah.
Yeah, absolutely. Thanks, Craig. If anyone has a question for Craig, I put a couple of notes in the chat on anything that you heard about today, the ARCMaster FSM-100P Plus or the FPS software. Please type that question into the question box directly. We'll get it answered. If not, Craig will go back through afterwards and send everyone an email with a digest of the questions and the answers. But I'd like to bring in Mega Garalapati. He's a product manager in our Splicer group here to help with the Q&A. Mega, we had a few come in.
Thanks, Charlie. Yes, Craig, amazing presentation. It is always fascinating to see 100 working with Panda. Here we have some very elaborated questions, but apologies for others out of time. We cannot really go through all questions, but we'll start with a few. How did you adjust the LED power? That is one of our questions.
Yeah, so the LED power so I'm assuming this is during end view imaging. And I did touch on this very briefly, but the end view, so if you're in the end view alignment state, right, where you're looking at the end of the fiber, if you hit the question mark, right, it'll toggle the controls for the end view alignment, right? You can switch between motors using the left and right keys, and drive the motors using the up and down keys, toggle your alignment grid using the escape key, and toggle between fine and coarse motor steps using the enter key, right? And so those are all your motor functions, but you asked about the LED function, right? So you toggle between motor drive and LED adjustment using the menu key in the end view alignment mode, right? So you just hit the menu key and the splicer will move to adjusting the end view LED brightness, and it'll usually pop up on your Y camera side as text of showing the LED brightness in bits, right? It is a digital machine, and so digitally, the machine understands the LED brightness in bits, and so the maximum bit brightness is 1060 bits all the way down to 0. So, and that's adjustable on either side.
Awesome, thank you. And we have another question basically asking, they installed a FPS 2.05 and presently we are using 2.09. So will the software automatically check for updates once installed, or do we need to reinstall the entire software?
So currently the software will need to be reinstalled. However, we are working on functionality for that sort of auto update checking to be implemented in the future. So you don't have to go through, okay, uninstall 2.0.5, reinstall 2.0.9. So we're implementing that in the future. It's not currently implemented, but we're working on it.
Okay, perfect. If the electrodes come into view during splicing, is that wrong? And how would one correct it?
So this can depend on a lot of things. If you use the vertical height offset in the splice mode, that can cause the electrodes to come into view if you have a narrow electrode gap. For instance, if I keep my 1 millimeter electrode gap, then what's going to happen is if I drop the electrodes all the way down, right, so my electrode vertical height offset so what it'll do is it'll actually move the V grooves up and down, right? It'll move the V grooves up to create a lower offset compared to the electrodes, right? So the electrodes are below the fiber, and it'll move down to put the electrodes above the fiber, right? You can move the electrodes up to 100 microns above the fiber or 200 microns below the fiber, right? And if you move it all the way below the fiber, right, then what happens is those electrodes do come slightly into the field of view, right? And that can interfere sometimes with alignment, right? Specifically with rotation alignment, because the splicer is looking for a certain focus position. If there's another object in the field of view, that can mess with the splicer. And so the first thing I would say is maybe adjust the electrode gap and opt to use a special arc calibration instead of standard arc calibration, right? Do that. And what that'll do is if you physically spread the electrode gap out, that will move the electrodes out of the field of view and keep that from being an issue. But if you're in the standard state, like splicing a regular single mode 125 micron fiber with a 1 millimeter electrode gap, you should not see the electrodes in the field of view. If you do see that, that's an alignment problem, and the splicer most likely needs to be sent in to be adjusted. However, I would say just really double check and make sure there aren't any settings that could be causing the electrodes to be seen by the camera.
Awesome, thank you. And,
so real quick before the next question, we're finished with the splice. I'm going to show you the data that we captured, right? So I'll hit collect data, single, right? I'm collecting just the data, not measured loss, and I'm collecting the IPA data, right? So now I'm seeing all my loss numbers. These are all estimations, right? Because I'm not using any measurements. On my IPA data, this is what my splicer measured after the splice, right? I can see my left is the blue line, my right is the red line, right? And we can see each core indicated by a peak and the marker indicated by this valley that denotes the asymmetry in the space between these peaks, right? So I've got my alignment. This is what happened before the splice, basically where it started versus where it ended, and then after the splice, we perform the estimation. Okay, just wanted to show you that. This is what we just did, right? This is the splice we just did. So sorry for interrupting, Mega. Go ahead with your question.
No, you're good. You're good. Also, to note, we also have the live zoom in the data. We can basically see any smaller troughs, so that you can see much more many data points in one single place. I have struggled with getting a good end view image on particular fibers, generally ones with darker color coding. Are there any known ways to help with this one?
So the fibers with colored coatings do tend to cause issues with end view imaging, simply because that color coding will either absorb or reflect the injected end view light. And a lot of times you'll have to turn the brightness on the end view LEDs all the way up just to get an image on the splicer. What you could do, and this would be very time consuming, but you could strip some of the fiber behind the fiber holder and then recoat that specific spot, or find some sort of polymer that is, or polymer or acrylate or something that has the correct refractive index to function as a coating, right? But also is transparent, so that light can be injected through that new coating and into the cladding, so you can get an in-view image. Now, if this would be for a production use, that's kind of impractical, and it may be more effective to use a power meter or a polarimeter for rotation alignment. But I don't know if that's helpful, or if it's makes things more convoluted. Does that help?
Yes, thank you. Yes. And due to time constraint, we have several other questions, but we cannot really go through each one right now. So I would request everyone to hold off. Please send your questions if you have anything else. Please reach out to your nearest salesperson or our technical support team, AFL support team, and we can surely answer each and every question you guys have on our FSM-100P Plus and our FPS software and all different factory splices we offer. Anything to add, Craig?
No, thank you everybody for your time and attention. I hope this has been informative and you can get some good information out of it to make your splicing work better for you.
Yeah, thank you very much, Craig. Hopefully we can convince you to put out a digest. There were lots of questions that came in, and maybe you can take a few minutes to answer some of these, and we'll send it out to all the attendees if you're
Sounds good.
Willing to do
I'll
that.
definitely go through them.
All right. Thanks for your presentation, Mega. Thanks for the Q&A help. Thanks, everyone, for joining in and the questions today. We will send out a survey after. We appreciate all of your comments on this and the future webinars. A link will also be sent out tomorrow to the recording for viewing. So this concludes our webinar, and we hope you all have a good afternoon and a good evening. Thanks very much.
Yes, thank you.